My name is Dr. Maria Weber. I'm going to walk you through a circuit analysis problem, and in this one in particular, we have two batteries in our circuit, and we have a couple of different pathways for our current to go, and we have four resistors here too. So here we have two batteries. I'm calling V1 and V2. I have four resistors, R1, R2, R3, R4, and I've drawn in a direction for the current. I'm going to assume that what I'm going to call current 1 is running this direction along this middle branch here, and then it encounters this junction here and splits off into I2 going up and around this part, and then I3 going down and around this part of our circuit. And when these currents, I3 gets to over here and I2 gets to here, they combine and equal I1 back through this way. Okay, so we are going to solve this problem. What I'm looking for is to calculate what the currents I1, I2, and I3 should be in the circuit. Now, in order to do that, we are going to start with three basic equations. We have three unknowns. We need three equations to find those unknowns. Now, whenever I do circuit analysis, I always refer to Kirchhoff, and we want to think about Kirchhoff's two rules. Now, Kirchhoff's first rule is sometimes called the Junction Rule, and that says that the sum of all of my currents coming into my junction must equal the sum of all of my currents coming out of the junction. So if I'm looking over here at this particular junction right here, I see that current I1 has to equal I2 plus I3, and I'm going to call that equation 1. Okay. Now for my second and third equations, I'm going to refer to Kirchhoff's second rule. And that's sometimes we call it the loop rule, and that second rule says that the sum of all of the potential differences that we encounter around a loop that we can draw in our circuit must equal 0. Okay, and so I can draw in two loops that I'm going to follow through, Kirchhoff loops, in the circuit right here. And I always like to start my Kirchhoff loops at a power or at an EMF source if we have them in there. So I'm going to start here with my battery, which I'm calling V2, and that's where I'm going to start drawing my Kirchhoff loop for this top loop here, which I'm going to call loop 2. And so this loop going to start in this direction, and it's going clockwise around this upper part. And we're going to call this one loop 2. Okay? And then down here, I'm going to draw my second loop, starting from this battery right here and going counterclockwise, opposite the direction of the clock, and I'm going to call that one loop 1. Okay? So if we start with loop 1 and apply Kirchhoff's second rule, this is what it looks like. So if we start here at our battery V2, as we're moving along the loop from the negative to the positive terminals of our batteries, we increase our potential. And so we're going to call that a positive value for V, and I'm going to refer to that as V2. Okay? And now as we go through this direction here, I'm going to go around my loop in this direction, and then I'm going to encounter here resistor 4. And as I cross through resistor 4 in the direction of my current I3, I'm decreasing my potential. And as I decrease my potential, I'm going to refer to that as a negative value for my potential as we go across through here, since we're decreasing that potential. And so the potential that we drop across R4 is going to be current through R4 times the resistance, because if we think about Ohm's law, the potential equals the current times the resistance. V is equal to IR. So we can represent that potential difference drop across R4 as minus I3 R4. And then as I continue around my loop, I'm going to go up this direction, and I'm going through here resistor 3. And as I move through resistor 3, I'm again decreasing my potential. Current run is 1. What I'm calling current 1 is running through resistor 3. So I'm going to represent that potential decrease drop across here as minus I1 R3. And that all has to equal 0. And that is what I'm going to refer to as my second equation. Okay? And now we've got our final equation that we're going to write here. We've got the junction rule loop 1, and now let's do the equation for loop 2. So I start here at loop 2. I'm starting at my battery source V2, and I'm increasing my potential as I grow across there. So I'm going to say V2 minus, I'm going in the direction of current through resistor 1, minus I2R1. Okay? And then in the direction of my loop, I'm going from the negative to positive terminal of V1. That's an increase in potential, so I'm going to call that positive V1. And then I'm going to go through loop 2, through resistor 2 with current I2. So I'm going to refer to that as minus I2R2. And then I have one final resistor to move through. I'm moving through loop 2, resistor 3, in the direction of the loop, in the direction of current I1. And so I'm going to call that minus I2R1, and R3. Sorry, minus I1 R3 for that one, minus I1 R3, and that all equals 0. Okay, and I'm going to call that equation 3. Now let's double check that I've got these equations here correct. Okay, all right, so now the next step, what I recommend is that instead of solving these problems algebraically, which you absolutely could do, what I'm going to recommend is that instead you just go ahead and plug in our numerical values right now. And it's going to make our problem-solving process, in this case, I think, a little bit simpler for us. So let's start over here with equation 2, and let's go ahead and plug in the values that we have. So I've got V1 is 10 volts, V2 is 12 volts, R1 is equal to R2 is equal to 4 ohms, R3 is equal to 8 ohms, and R4 is equal to 2 ohms. Okay, so then if we go back over here to equation 2, we've got V2 is 12 volts, and I'm going to skip putting in the units here. So V2 is 12 volts minus resistor 4 was 2 ohms, so minus 2 I3 minus R3 is 8 ohms, so minus 8 I1, and that equals 0. Okay. Now what I'm going to do is I'm going to solve this equation right here for I3. I'm going to solve it for I3, and we'll get I3 in terms of I1. So I can add 2I3 to the other side of my equal sign. So 2I3 is equal to 12 minus 8I1. Now I divide both sides by 2, and when I do that, I3 is equal to 6 minus 4I1. So now we're left with our equation I3 is equal to 6 minus 4I1. I'm going to call this equation 4. Now let's move over to our equation for loop 2 and fill in the values for there. So V2 is 12 volts minus I2R1. R1 is 4 ohms, so minus 4I2 plus V1 is 10 volts minus R2 is 4 ohms, so minus 4I2 minus I1 R3. Resistor 3 is 8 ohms, so that's going to be minus 8I1. That all equals 0. Now I'm going to combine the 12 and the 10, so that's 22. And then I've got my minus 4I2 and minus 4I2, so I'll put those together. That's minus 8I2 And then I have my minus 8I1, that equals 0. Now I'm going to solve this equation and get I2 on one side of the equation. And so if I do that, then I have that 8I2 is equal to 22 minus 8I1. So I've taken negative 8I2 and I've added that to the other side of my equal sign. Now I divide both sides of my equation by 8. And then I have that I2 is equal to 22 divided by 8 is 2.75 minus 8 divided by 8 is 1, so minus I1. And I'm going to call that equation 5 right here. Okay, so now now we have equation 4, which has I3 in terms of I1. Now I have equation 5, which has I2 in terms of I1. So I can take these equations, 3 and 4, and substitute them in up here to my first equation, equation 1. Okay? And so if I do that, then I have that I1 is equal to I2 was 2.75 minus I1. And then I3 was 6 minus 4 I1. Okay? And so then I have that I1 is equal to, if I add 6 and 2.75, that's 8.75. And then I have minus I1 plus minus 4 I1. So that's minus 5 I1. And so I have now that I1 is equal to 8.75 minus 5I. So I can add this term to the other side of my equal sign, and then I have that 6I1 is equal to 8.75. Divide both sides by 6, I get that I1 is equal to 1.46 amperes. Okay, so now that I've gotten one of my currents, I can take that current, and because we solved equation 4 in terms of I1 and equation 5 in terms of I1, I can just go ahead, take I1 and plug it back into equation 4 and 5, and then I'll get what my currents should be for I3 and I2. So if I go ahead over here and say I3 is equal to 6 minus 4 times my 1.46 amperes, then I find that I3 is equal to 0.17 amperes. Okay? And then over here, if I do 2.75 minus 1.46, I get that I2 minus 1.46, I get that I2 is equal to 1.29 amperes. Okay? Cool. So then if I combine I2 plus I3, I'll get back again I1, my 1.46 amperes. So that would be equation 1. If I took I2 here, I2 plus I3, added them together, I'll get back my current here, I1.